All right, the long anticipated lecture, Chapter 10, Inductance. This is going to be an unusual property for us to discuss compared to what we've talked about up to this point. What we've talked about up to this point really is conductance, resistance, period. In discussing inductance, you're going to see that things with inductance change over time. Okay, the property actually changes. The influence it has on a circuit changes over time. So you're going to see that this is very dynamic, literally dynamic component and property. Chapter 10, Inductance. After completing this chapter, you're going to be able to explain the principles of inductance, identify the basic units of inductance, identify different types of inductors, determine the total inductance in series, parallel circuits, explain LR time constants and how they relate to inductance. Now, the property of inductance is that characteristic of an electrical conductor that opposes a change in current flow. Opposes a change in current flow. The symbol that we use is the capital letter L. So in a circuit, if you see on a schematic diagram L equals, that means inductance is equal to whatever specific amount is identified. Now, an inductor is a specific device designed to possess this property of inductance. An inductor is a device that stores energy in a magnetic field. And it's important for us to understand this property because we're going to counter this next chapter when we talk about capacitance, right? I'll let the cat out of the bag. Capacitance is an electrostatic field. Inductance is an electromagnetic field. That's what's the magic behind an inductor. Now, once current is moving through a conductor, inductance helps to keep it moving. As the magnetic flux lines build up, they create an opposition to the flow of current. An opposition to the flow of current. Lenz's law talks about that. Lenz's law states an induced EMF in any circuit is always in a direction to oppose the effect that produced it. The amount of counter EMF is proportional to the rate of change. The faster the rate of change, the greater the counter EMF. So what this means, let's go back, last chapter that we talked about. Remember magnetism? Remember when we pass current through a conductor, we create a magnetic field? Lenz's law says if the current was going that way, it's going to create an electromagnetic field like this. Make sense? If we shut the circuit off, that electromagnetic field is going to collapse, and it's going to produce a counter electromotive force that goes that way, the opposite way of what created it. So if the EMF goes that way and it creates some magnetic field like this, the magnetic field collapses, it creates a counter EMF that goes in the opposite direction. So the second part there talks about the rate of change. The faster we turn that on and off, on and off, on and off, expand, collapse, the faster we do it, the more pronounced that effect is going to be. If you connect one of them there, inductors, to a DC circuit, it's going to happen once when you close the circuit and energize it. And when you de-energize it, that field's going to collapse and create that countercurrent. So it's only going to happen once. It's going to expand once and it's going to collapse once. Now I'm going to let out a little secret because you guys have all read ahead AC. What's one thing that's constant about AC? It's constantly changing. Very good. Constantly changing. So the higher the AC frequency is that we apply to one of these devices, the more pronounced this effect is going to be. Does that make sense? Goes back to Lenz's law. And again, anytime that in class I say anything about a law, we should like ring a bell, dim the lights, hit some chimes, you know, hit a gong, because laws you could take to the bank. You answer a question on your quiz using a law, on an exam using a law, you approach a project or a lab assignment using a law, you're going to get good results. Now, inductance is measured by the Henry, and this was invented by a guy whose name was George. Guy by the name of Joe Henry, my main man. Henry, ironically, is abbreviated with the letter H. And 1 Henry is the amount of inductance required to induce an EMF of 1 volt when the current in the conductor changes at a rate of 1 amp per second. So 1 Henry is equal to 1 volt of EMF at 1 amp per second. 1 is equal to 1 over 1 over 1 second. Now in electronics, the typical values that we're going to see will be the millihenry times 10 to the negative third, the microhenry times 10 to the negative sixth. In some high power applications, you may see henries. But generally speaking, most of the stuff that we're working with in microelectronics, millihenries, microhenries. Now, inductors are those specific devices designed to possess the property of inductance. So they're designed to have a specific inductance. That's why come they be invented. They consist of a conductor coiled around a core. Remember, if we got like X amount of magnetism by creating 1 turn, how much would we get if we make 2 turns? Twice as much. It's that simple. It's easy math. Consists of a conductor coiled around a core, and it's classified by the type of core material, whether it's magnetic or non-magnetic. If we use a magnetic core material, we're going to get a higher amount of inductance out of it. If we use non-magnetic, we're going to get a little bit lower out of it. So sometimes they'll use that core material to get it just, not too much, not too little, but just right. This is the schematic diagram for a fixed inductor. And for those of you out there that want to go home and roll your own, you could do that. You just need magnetic wire. Magnetic wire is basically thin copper wire, solid core that has a lacquer coating on it. If you've ever looked into a transformer or a motor and you see the windings, that's magnetic wire. That's all you need. Some cases you don't even need magnetic wire because you could roll a coil, and as long as the wires aren't touching each other, you're using air as an insulation, you could roll your own. I've been known to roll my own on a few times with mixed results. I have no idea what I'm talking about. Actually, I know exactly what I'm talking about. This is a variable inductor created with an adjustable core material. Now, the way they come up with this is pretty fascinating. What they'll do is they'll get a ferromagnetic core material typically, like powdered iron, and then they basically form it into a material, press it into a material, and then they thread it. And then they thread the center of the core. And what you could actually do with it, right, is righty-tighty, lefty-loosey, screw it in, And as you screw it in, what are you doing? You're increasing the magnetic influence of the iron core. So by simply adjusting that, this is used for fine tuning in a lot of circuits that contain these. Very fine, subtle tuning. Another thing that you could do, and I used to see this old school, not as much now, they would use a brass insert. And when you screw brass in, what are you doing? Brass has a high level of reluctance, so it's going to oppose that magnetic field. So by screwing it in, you're lowering the amount of inductance. If it was iron core and you screwed it in, you'd be increasing it. So it's counterintuitive. And it gets worse. Because what would happen is typically the questions that I used to be asked in a lot of my military, Navy equipment schools, what we would have were circuit card extenders. So what you would do is take the circuit card out, put it in the extender, and then now the circuit card was mounted above the rest so that you could get in there and make adjustments. A lot of times you'd have to make the adjustments from the back side. They'd have a little hole physically in the board that you could put your adjustment alignment tool in. So then they'd ask, if approaching it from the back side, which direction need you turn the inductor to see a decrease in inductance? So it's one of those things that, you kind of, let's see, if I'm turning it clockwise from the top, that's going to be counterclockwise from the back side, but it's brass core, so as I'm turning it counterclockwise, I'm really moving. I mean, it's just these questions that like you thought your head was going to explode. But you know what? You kind of had well, I don't see how that really ever helped me in life knowing that stuff. Because basically when you got out to the fleet and you put a circuit and you set up your test fixture, and basically as soon as you start turning it the wrong way, you see needles go the wrong way. And you turn it back and you get it to where it needs to be and you're done with it. You don't sit there and, well, let's see, if I approach, and if I'm using a mirror, I'm actually seeing the inverse. I mean, just crazy stuff. But think about that, because these still, and some of you may work on some legacy equipment. It's fun to repair legacy equipment, to retrofit, to do things like that. So you may end up finding some of this stuff. This is my personal collection of inductors. You guys actually believe me. This is an air core inductor. This is a fixed value inductor, and that's all it is this wire wound around a magnetic core. That's all it is. All of these can type here are adjustable. And actually, if you could look here, this almost looks like this takes a hex head, right? Like an Allen head. Whatever you do, don't use an Allen wrench to try to adjust this. Because typically the Allen wrench in your toolkit is made out of iron, steel, ferromagnetic material. So as soon as you get it in close proximity and you adjust it and get it just so, you're going to remove part of the magnetic influence and your numbers are going to go cattywampus. So all of these need to be adjusted with non-magnetic alignment tools. I've got a tool roll at home from back in the day. I should bring it in as an example. It's this big tool roll. It's like every alignment tool known to humankind. And they're basically all plastic heads. The other thing too is, you stick your a hex head in there, you stand a chance of damaging that. And even if you break off a little bit of material, that amount of material was designed, engineered to be there to create X amount of magnetic field. So you kind of gotta get it right. So don't start, if you don't have the right tool, don't touch this stuff. So it's typically called an alignment tool, or actually a tweaker in the classical sense of the word. A tweaker. And you could always tell who the technicians were, because they'd always have the tweaker in their pockets. And you knew, it's kind of funny. back in uniform, submarine base in Connecticut. I'd be walking around. I'd see you with a tweaker in your pocket, you know, at the deli or whatever, and I knew exactly what you did for a living. It's the only guys running around, only goofballs running around with tweakers in their freaking pocket, or electronics techs that were regularly aligning equipment. Air core. This is an inductor. Well, not without core material because it has air in the core. That's why it's called air core. It's used for values up to 5 millihenries of inductance, wrapped on ceramic or phenolic core. In this case, it was probably wrapped around a dowel or something and then removed, and it has form in and of itself. This is actually a really good photograph because you could see the magnetic wire here, and you could see where the insulation has been stripped. This is bare wire, and then this is insulated. A lot of times people see this and they think that it's bare wire. It's not bare wire. It's insulated. One of the best ways of getting this insulation off, if you're going to do a lot of this, is with a chemical stripper. Chemical stripper. And basically it's like a thinning agent. You dip it in, paint thinner, paint remover, and it removes that right down to the metal, and it makes it solderable. You have to put a neutralizing agent on it, but that's the best way of doing it. Other than that, you know, you're going to get your wire strippers, and your wire strippers are just basically going to scratch the stuff off. It's not going to really, because this is a lacquer coating on it. But this is an inductor. Believe it or not, just a piece of wire making those 5 turns, it's going to give you X amount of inductance. Might be enough for you to get the job done. Question?
On the last air core picture that you had, there was a piece of metal going through it. What's that for?
This piece right here?
Yeah.
I think somehow this is mounted. This serves as a form somehow to keep the shape of it. I really don't know.
Usually they're hollow though.
Yeah. Oh yeah, yeah. This is not here to influence the magnetic or all. It's either there for aesthetics or to help the way that's mounted or what have you. It's a good observation. Some of these things are actually pretty cool looking. Again, when you get into some of that older equipment, they made it with a certain level of elegance, you know, and this would be an example of that. If you opened up an old, 1930s radio, you'd probably find an inductor that looks like that in there. It's 1970s radio, no, you're not going to find that in there. Iron core. Iron core could be either ferrite or powdered iron. It's a typo, not ion. Ion core. Captain, the ion core is melting down. Damn you, Scotty. That's why I'm not into drama, right? Not a very dramatic kind of guy. It's iron core. Used for values of 200 millihenries of inductance, typically, up to 200 millihenries of inductance. Schematic symbol shows these 2 parallel lines next to the coil. That shows that there's an iron core next to the coil. Toroid core, these are donut shaped, but do not try to eat them. They offer a high inductance for a small size. These are very prolific in a lot of contemporary electronic applications because the magnetic field is contained in the core, offers a very high inductance for a very small size. If you opened up a computer power supply, you'd find a bunch of these inside. A lot of inductance for a relatively small package. I've had graduates that have gone to work for companies and they had to do this as part of their job, roll their own. They're given the blank core, spool of wire, and you sit there and you thread it through and tighten it up, and thread it through, tighten it up, clean the leads, and solder it in the boards. Actually pretty good jobs. Most of the people that are playing around with this stuff are for RF applications, radio frequency, high energy radio frequency. Mr. Graham, what's going on, man?
Well,
Got a question? You're just back there waving, man. It's like,
Exactly. Shooting the evil eye.
What's up?
Magnetic field contained in the core, basically the significance of that is spray into things around it, right? It's just going to be contained in the core, as opposed to like a normal transformer is going to have a field around it.
Yeah. Yep, so it's not wasting that field going outside, it's containing it basically. Increases the efficiency, which makes it more better.
Yes. And it stimulates my hunger also.
This is a shielded core. Shielded core. Have a shield of magnetic material to protect them from the influence of other magnetic fields. Because if you've got a couple of these in close proximity to each other, one field could influence another device. Now, if you just saw this, if you didn't know any better, what would you think this device was? Now, it looks like a transformer. And the only tell that there is on this is there's only 2 wires. If you look on the other side, you wouldn't find any other wires. But it would look exactly like a transformer. As a matter of fact, you can use a transformer as an inductor. If you don't connect the secondary leads to the primary, if you only use just the coil, you could use a transformer as an inductor for some applications. That's why I've got a garage full of junk, because I won't throw a transformer away, because someday I may want to use it as an inductor. This is laminated core. And again, if you didn't know any better, you'd think it was a transformer. We know it's an inductor because there's only 2 wires coming out of it. And the top is stamped 4.5 Henrys, 4.5H. And this was going to vary from 0.1 Henrys all the way up to 100 Henrys. This is also sometimes referred to as a choke. As a choke. Used as a choke in automotive applications. Noise filters, meaning to choke off a change. It's going to choke the change. Just like resistors, inductors could be connected in series parallel or series parallel. When you're dealing with inductors measured in Henrys, in series, you treat them exactly like resistors, plain and simple. If I've got 2 Henrys and I put it in series with 4 Henrys, 2 plus 4 equals 6. I now get 6 Henrys worth of inductance. In parallel, you treat them like resistors in parallel. So the total inductance will always be less than the value of least, as long as you're dealing with the property measured in Henrys. Now this is where things get interesting. Everything else I've been talking up to this point has just been kind of, hey, just trying to get to know you. This, the real deal. This, DIS, is what it's all about. It's a series circuit. It's a series circuit. I've got a switch that has 2 positions. One is called the growth mode and the other is the decay mode. Okay, so this switch I could toggle from either growth to decay. When it's in the growth mode, I have a simple series circuit, do I not? And the circuit contains an inductor. Actually what? An iron core inductor, because I see the parallel lines to the inductor, in series with a resistor. Make sense? When I close the switch, as soon as I close the switch, it's going to allow current to flow through this circuit. Do you agree with me? What's going to happen is that current is going to come racing through the circuit, negative to positive, and all of a sudden it's going to hit this curly piece of wire. And that curly piece of wire it's hitting is an inductor. An inductor is a specific device designed to possess the property of inductance. Inductance is that property which tries to oppose a change in current. So current was at 0, it wants to go to 100%, and this device is going to say, I want you to stay at 0. Why? Because you've been at 0 and I like it like that. But eventually, as the current continues to come, that magnetic field builds and current eventually goes to maximum. It goes to 100% for this circuit. But the inductor, because of its property of inductance, is going to fight the whole time to try to prevent that change from occurring. But eventually it's going to lose. So close the switch, turn the circuit on. The inductor is going to fight, and eventually give up, and current's going to be at 100% flowing through this circuit. And by the way, when current is at 100% flowing through this inductor, electrons are like, what's up with that? It's a piece of curly wire. After a period of time, the electrons, it's like, why am I going through a piece of curly wire? It just has no effect on them whatsoever. And the circuit runs and runs and runs. Soon as we get the switch and move the switch from the growth mode to the decay mode, the magnetic field that was built up around inductor L1 is going to collapse. And it's going to collapse into itself. When it collapses into itself, what is it going to do? It's going to act like a... What happens when a magnetic field passes through a conductor? We induce current. If we move a conductor through a magnetic field, we induce current. If the conductor is stationary and the magnetic field moves through a conductor, we're going to generate current, right? So as soon as I move this to the decay mode, this magnetic field is going to collapse into itself, creating a counter current. Lenz's law, remember, the opposite of the force that created it. And then that current is basically going to flow through the circuit until it dissipates. But if this was just a series circuit made up of a resistor, and a switch, you turn it on, boom, you go to 100%. You turn it off, pow, you go to 0. Now, with an inductor in here, you turn it on, it's going to come up and eventually get to 100%. You turn it off, that magnetic field's going to collapse and eventually it's going to get down to 0%. You follow what I'm talking about? You guys know what I'm talking about. I'm beating around the bush. What am I talking about? Time constants. Time constants. The time required for current through a conductor to increase to 63.2%. So if I apply 100% to it and that first time constant, it's going to rise 63.2%. In the next time constant, it's going to gain 63.2% of what's remaining. The next time constant, 63.2% of what's remaining. The next time constant, 63.2% of what's remaining. The next time constant, basically after 5 time constants, we say enough is enough, it's 100%. But is it really at 100%? No, because it's nonlinear. So really, it never reaches 100%. We say after 5 time constants, it's reached 100%. It's good enough for what we do. To calculate out this time constant, it's actually relatively easy. LR is the symbol used for the time constant of an RL circuit. And the formula is T is equal to L divided by R, period. It's that simple. Take the amount of inductance, divide it by the amount of resistance. That's going to give you the time constant, measured in seconds. That's what we use as our base unit of measurement in electronics, the second. T is equal to L over R.
That would be for individual and total too, right?
Yes. If I gave you 4 inductors, you'd have to calculate out the total inductance and plug that in the circuit right there. So I could give you some real nightmare circuits right now. Think about it. It'd be fair game. I could give you a circuit that's got, 13 inductors and combination series parallel. and 22 resistors, combination of series parallel. The bottom line is it's equivalent to this circuit here. You've got to figure that out. But you should be able to do so without a whole lot of fuss. This is what a time constant curve looks like. Here's that first time constant, 63.2%, 63.2% of what's remaining, 63.2% of what's remaining, 63.2% of what's remaining, what's remaining. And what is it that I'm actually looking at here? What is this in blue? Is this voltage? What is this?
Current?
It's a current. Current, number one, because the slide says so. But number two, most importantly, because it's current that's going from 0. The inductor is trying to prevent the change, 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 trying to prevent the change. All right. Current wins. Then as soon as you shut that circuit off, current's going to try to go from 100% to 0, but because that magnetic field is collapsing, I don't want to decrease, I want to keep it 100%, but I can't, oh crap, all the way down to 0. But because that field is collapsing, it's going to try to prevent that change. That's why we use these. That's why we use these.
Can inductors affect voltage?
Absolutely. If we're affecting current, definitely will have an effect on voltage. In summary, inductance is the ability to store energy in a magnetic field. Just remember the key word for inductance is magnetic. That's how they do their magic. The unit for measuring inductance is the Henry, measured by the capital letter H. The letter L represents inductance. Inductors have specific inductances. That's why they're designed. The symbol for a fixed inductor is down here at the bottom. Symbol for a variable inductor has an arrow going through it. The arrow means it's adjustable. Types of inductors include iron core, ferrite or powdered iron core, toroid core, shielded core, laminated core. Formula for adding them up in series is like the same formula for adding up resistors in series. The only thing you need to be aware of, you're adding up inductance measured in Henrys. If it's not in Henrys, can't use this formula. The formula for total conductance in inductors in parallel is the reciprocal formula. Use it same as you would for resistors in parallel. Time constant formula, T is equal to L over R. You run this calculation, it shows you what one time constant is worth. I need to multiply that by how many to figure out how long it's going to take to get to 100%. 5, because it takes 5 time constants to reach 100%. So understand that when you do this math, you only end up with 1 time constant. It takes 5 to get the job done. Or as it says here, 5 time constants required to fully build up or collapse the magnetic field of an inductor. Any questions on anything that we discussed with the inductors? Yes?
I'm still a little vague on why they have inductors. I mean, other than the fact that they create inductance.
Yep, and that's it. We have inductors because they create inductance. And inductance is that property which tries to oppose a change in current. So we're going to have a lot of different components that are going to want to bring about a change in current in a circuit. And if we put an inductor in there, an inductor could help stabilize that current flow because of that electromagnetic property. So it's going to help stabilize current levels in a circuit. The majority of applications that we're going to use inductors for is really going to be filtration. Because once, we're not there yet, some of you may have read far enough ahead, that when we apply an inductor to an AC circuit, it starts doing some wacky stuff. And by harnessing that wacky property called inductive reactance, we can use that to filter. We could use it in audio applications where we want only certain frequencies to go to certain speakers. Heck, I knew a guy that was getting some interference on one of his cable channels back in the day. And because this friend of mine had extensive electronics background, he didn't want to call the cable company and have them waste their time and come out and... Exactly. So this friend of mine built a filter circuit to filter out the garbage signal that somebody was putting on this pay-per-view channel. And by filtering out the garbage that got put on the channel, the reception was enhanced and made the station viewable. And the key component in that whole, so I'm told, project is an inductor. And ironically, it was an inductor that was like 3 turns of wire. 1, 2, 3 turns of wire was adequate enough for the reception to be enhanced. Mind-boggling, so I'm told. Question?
Some of us old fossils that were welding 40 years ago, like welding on sheet metal is always a problem, keep them blowing through.
Yeah.
So we just take one of the cables and kind of like you would do a garden hose or on the deck of a ship, just coil up a line. That would gentle things out enough that you could strike an arc and not blow.
Oh, really? Interesting.
So obviously we were making an induction.
Yeah.
Air core.
Yeah. And little did you realize what you were doing at the time.
It just worked.
Yeah. Nobody knew why, but it worked. Now you know. All right, let's go ahead and take a break. And at about 6:20, we'll start up with Chapter 17.